Hello and welcome. This is the Math 108 Algebra for College Students final exam review. If you are watching this particular video, then that means you are in my Math 108 course and you are trying to prepare for your final exam. I am hoping that this exam review actually helps you out, kind of gives you an idea of what is on it, and I'm just going to work through each of the examples here so you can kind of see what I am expecting. So let's go ahead and get started. So this first question we see here is a basic order of operations example. And so what we want to do here is make sure that we understand and follow order of operations in order to work it out. So first thing that we need to do is work out the expression that's in the most inner grouping symbol, which is these parentheses here. And so we see it's just 13 minus 10, which is just 3. And then we'll do that minus 18 all over. And then we know that 3 squared is 9 minus 3. And so from there, the next thing we could do in the numerator is multiply. And so we'll multiply 36 times 3. And so believe that should give us 108 because 6 times 3 is 18. So we have 8, carry the 1, and 3 times 3 is 9, plus 1 is 10. So that's 108 minus 18. And of course, 9 minus 3 is 6. And going from there, if we take 108 and subtract it from 18, we should get 90. Divide by 6, and of course 90 divided by 6 would end up being 15. And so that is our first answer. So let's move on to question number 2. All right, so for question number 2, we're asked to solve this linear equation. And so if you notice, this linear equation has fractions. And so I'm actually going to do this 2 ways. The first way that I'm going to do it is I am going to do it by finding the lowest common denominator, which in this case would be 4. In between the denominators 4 and 2, multiplying both sides by the common denominator to get rid of the fractions, and then from that point solving it like it's a linear equation. The second way that I'm going to do it is I'm going to do it dealing with the fractions. So I'll still be finding an LCD, but in doing that I will deal with the fractions all the way through. Okay, so the first way is I'm just going to use the LCD to clear out our fractions. So we notice here our LCD is 4. And so what that would mean here is that we're going to multiply both sides of our equation by 4. And so I'm just going to do it like this. Okay, so whenever we go and distribute the 4 to both terms, then of course we have 4 times 3 over 4, x, plus 4 times 3 over 2. And of course this would just be 4x divided by 2 if we multiply that together. And remember here that when we say 4 here, that's like saying 4 over 1. So we multiply numerator with numerator, denominator with denominator. If you notice here, 4 times 3 is 12, and 12 divided by 4 is 3. So you could look at it that way, or you could say that 4 and 4 reduce to 1, and you're just left with 3x. Same deal here, 4 times 3 is 12, 12 divided by 2 is 6, or you could just say 4 goes into 2 goes into 4 2 times, and 2 goes into 2 1 time, and you just have 2 times 3, which is 6, 6 divided by 1, which is 6. And then of course here, same deal, 4 divided by 2 is 2. So we just would reduce it like that, and 2 times x divided by 1 is just 2x. So from that point, we need to get everything with x on one side, everything else on the other. So we're going to subtract 2x from both sides, and that will cancel to 0. 3x minus 2x is just 1x, which is just x, plus 6. And then we can subtract 6 from both sides. That cancels to 0. X plus 0 is just x. And then we have 0 minus 6, which is a negative 6 on the right side. And so from there, we see that that would be the answer. Okay. If we actually were dealing with this with the fractions, this is what it would look like. For those of you that are a little bit more comfortable in dealing with that. So the first thing that we would want to do here, again, is realize that we have common denominator of 4. And so to change all these fractions here to have a denominator of 4, what we would want to do is multiply the numerator and denominator of this fraction by 2, as well as multiply numerator and denominator of this fraction over here by 2 as well. And if we do that, we end up with 3/4 x plus 6 over 4 equals 2x over 4. And so from that point, of course, we still want to do the same thing as we did right here by getting everything with x on one side, everything else on the other. So we will subtract both sides by 2/4 x, or 2x divided by 4, however you want to look at it. That cancels to 0. And here we have 3/4 x minus 2/4 x plus 6 over 4. And so from here, 3/4 x minus 2/4 x is just 1/4 x. And then from here, we can subtract 6/4 from both sides. That cancels to 0. And we have 1/4 x minus 6 over 4. And then, of course, from here, we could finish out by just saying that we can multiply both sides by 4 here. So you see, we still end up having to do that anyway. And of course, that reduces to 1 here. That reduces to 1. And we get x is equal to -6. So either way you look at it, you see that we end up having x equals -6 as the answer. Now we'll move on to question number 3. All right, so the next question asks us to take this formula and to solve it for the variable r. If you don't recognize what this formula is for the new value or accumulated value whenever you're using simple interest. And so simple interest is calculated just as I is equal to PRT, where P is the principal, or the amount that you borrow, or the amount that you lend if you're actually the lender instead of the borrower. R is your interest rate, and T is your time, always in years. And so whenever you're doing simple interest, of course, if you want to know what is the new value, you take whatever you initially borrowed or lent out plus the interest, and you end up having that. And if we write I is equal to PRT, we see that that's what that formula actually is. And so what we're trying to do is rearrange this formula so that we can find out what the interest rate would be if we had all the other pieces of information here. Okay, so we're just going to rearrange this as best as we can. And I'm going to go ahead and erase this, and then we'll start actually doing the problem. Okay, so one way we could do this problem is to start off just by subtracting both sides by p here. And if we subtract both sides by p, then that cancels to 0, and we just have PRT there, and this is a minus p. And then since we're trying to solve for r, we want to get rid of, so to speak, the p here and the t there. And so the easiest way to do that is just to divide both sides by pt, and we end up canceling those to 1, canceling those to 1, well, reducing those to 1, I should say, and we have r there. And so that is one way that we could actually work that out. Of course, if you wanted to, you could go a little bit further and you could form this into two separate fractions and say this is a divided by p times t minus p over p times t equals r. And if you notice, those p's would reduce to 1. So you would just have a divided by pt minus 1 over t equals r. Okay. So if you're looking at this for the exam, this is far enough. If you wanted to take it to this point, that is okay. What I'm going to be looking for is everything up to here if you do it this way. If you want to do it another way, what we could do is we could factor out the p out of both terms first, and when we factor it out, that will leave a 1 there plus rt. And then after that, we would divide both sides by p, since this is p times all that. And we would end up with this. And then from here, we can subtract 1 from both sides. And so that would be a over p minus 1 equals rt, because that would cancel to 0. And then the last thing that we would do is divide both sides by t. And that would reduce to 1. That would be r. And this would be a over p minus 1, all that divided by t. And this is another form of this answer here. And so if you're wondering how this becomes what we have over here, all we would have to do is take this answer that we have here and just multiply numerator and denominator by p. And so if we did that and distributed the p in the numerator to both terms and the p multiplied that times the t here, we would get this actual answer. Okay, so that's several different ways of doing problem number 3. Now let's move on to problem number 4. Okay, so example number 4, or problem number 4 rather, is a word problem. And so we see here that it says that the code to unlock a safety deposit box is 3 consecutive odd integers whose sum is 111. And we want to find those integers. So the first thing that we want to do is recognize that this is asking us for 3 consecutive odd integers. So if we started to list odd integers, 1, 3, 5, 7, 9, so on, we see that the difference in between all those numbers is 2. So we want to come up with 3 different numbers that add up to being 111. So we need to start off by saying x is going to be our first odd integer. And so now that we know that the second number, because remember, we don't know what x is, but we're trying to find that out. Whatever is going to be that second number is going to be 2 more than that. So that's going to be the second odd integer. And then, of course, 2 more than x plus 2 is x plus 4. And that will be the third. Oops, wrote that kind of weird. So the third odd integer. And so now from that point, we see that if we take this number, and this number in its form in terms of x, if we add all those together, the sum should be 111. So if we say x plus 2 plus x plus 4, that will all equal 111. And so since we just have addition here, we can go ahead and drop the parenthesis. And so then from there, it's just a matter of combining like terms. So we put letters with letters, numbers with numbers. So we have 1, 2, 3 x's being added to each other. So that will give us 3x. And of course, we have 2 plus 4 here will give us 6. And that will end up being equal to 111. Okay. And so now from there, we just solve this like how we do any regular linear equation. We subtract both sides by 6. That cancels to 0, and then we just have 3x on the left side. And of course, we have 105 on the right side. And then from there, to find out what x is going to be, we just divide both sides by 3. Of course, that reduces to 1 and just gives us x on the left. And if we divide 105 by 3, we know 3 goes into 10 3 times with a 1 remainder, and 3 goes into 15 5 times, and we get 35. So that means our first odd integer is 35. The second one, which would be 2 more than that, is 37. And the third one, which is 2 more than 37, is 39. And so these are the numbers for the code of the safety deposit box. Okay. Or you can just say 35, 37, and 39 are the integers. And that would be enough to answer the question there. Okay. All right, so we'll move on to example number 5. Okay, so for this question, we're asked to graph the linear equation that's given to us, which is negative 6x minus 18y equals 18. So we want to graph that linear equation by finding and plotting its intercepts. And what we mean by that is x and y intercepts. And to get full credit for the problem, the 2 points you must identify on the graph must be intercepts. Okay. In other words, you need to state what the ordered pair is for the x-intercept and the y-intercept here and here. And you must also write the x-intercepts as an ordered pair. So in other words, you have to identify what they are on the graph as well as give what the ordered pair is here. Now, the first thing we want to notice is that this line or equation of a line is in standard form. Okay. And so there's a couple of things that we know about standard form. We know that if we were to solve this for y, this would end up looking like this. Okay, and so we talked about that in class. Just quickly, just in case you may have forgotten, if we subtract both sides by ax, then that is just b times y equals a negative ax plus c. And if you divide both sides by b here, of course, that reduces to 1. You just have y here, and you have this, where this part here is your slope, and this part here is your y-intercept. So if you were wanting to rewrite this as y equals mx plus b. Now, you can do this in order to find out how to draw the line, but to me, that would be the hard way to do it. And so I went ahead and did this first just to kind of tell you that this is not the best way to go about trying to draw this particular line here and identifying where the x and y intercepts are. Okay. Now, note that c over b is going to tell you where the y-intercept is, but we don't have a direct way by solving for y to tell us what the x-intercept is. So that's why we want to take a different approach here. So I'm going to go ahead and erase all this and actually show you that as long as we have 2 points, namely if we can find the x-intercept and the y-intercept easily, then we could go ahead and have our 2 points to be able to draw the line and satisfy our other condition of stating where our ordered pairs are for our x and y intercepts. So I'm going to erase this now, and then we're going to go over that strategy of, okay, so now that we have that erased, the way that I recommend that you go about doing this is realizing that an x-intercept is you basically solve for x when y is 0. And here, for the y-intercept, you let x equal 0 and you solve for y. And so here we're just going to get our ordered pairs. So to solve for the, let's say, the x-intercept, we let y equal 0. So I'm going to come up here and do that. So if we let y equal 0, then that would be a negative 6x minus 18 times 0, which is equal to 18. And of course, all of that is equal to 0, which just means that a negative 6x is equal to 18. And if we divide both sides by a negative 6, we see that x just ends up being negative 3. So that means that a negative 3 would go here. And thus, your x-intercept is the point negative 3, 0 on your graph. And if you look, that would be right here if you were drawing. And I'm going to draw that a little better. Let's see if I can't get that to work. Okay. And so negative 1, negative 2, negative 3, 0 would be right there. So that would be where your point would be. And so now we do the same thing for the y-intercept. So when to find the y-intercept, we let x equal 0. So I'm going to come down here and do that. So negative 6 times 0 minus 18y equals 18. Of course, that goes to 0, which just leaves us with a negative 18y equals 18. And we divide both sides by negative 18. And we see that the negative 18 is reduced to 1 and just give us y. And 18 divided by negative 18 is a negative 1. And so that's what belongs here. And so our y-intercept is the point 0, negative 1, which would be right here. And so now all we have to do is draw a line going through both of these points. And of course, in general, that is what your line would look like. And so this is all you need to do on this particular problem. We'll go ahead and move on to problem number 6 now. Okay, so problem number 6 asks us to find out the equation of the line that passes through the point negative 3, 1 and the point 1, 6. And we're asked to write this in the form of y equals mx plus b, which is the slope-intercept form. So one thing I want to go ahead and make sure that you know now, if you're actually looking at the short answer sheet before you see all these problems worked out, what you're going to see is the answer given in standard form or general form. The reason why you see that is because that answer was computer generated, but that's one of the reasons why I went ahead and worked this out for you, because I want you to see how to actually answer this in the form that I want you to answer it in. And I do want you to answer it in the slope-intercept form. Okay, so the first thing that we know is that we only need 2 points or the slope in 1 point to come up with an equation of a line. Since we have 2 points, then we can label this point x1, y1 and label this x2, y2, and we can find out what our slope is by doing y2 minus y1 over x2 minus x1. And of course, we'll just plug in what we've labeled. It does not matter whether you have labeled this x1, y1 and that x2, y2, or if you reversed it and say that this was x1, y1 and x2, y2. Doesn't matter. As long as you start with one being x1, y1, just label the other one x2, y2, and you'll be okay. So now we have our x2 is 1 minus our x1 is a negative 3. And please note that since that's a minus and since that's a negative, how I've put the negative 3 in parentheses to respect the fact that this is subtract a negative number, which we know is going to end up being addition here. Okay. Of course, 6 minus 1 is 5. So we end up with the answer of 5/4. And so that is what our slope is. So now that we have the slope, we can either use the slope, in either one of these points to be able to find the equation of a line. And we could find it by using the slope or the point slope form this way, or we could use it by directly substituting everything into the slope-intercept form. I'm going to work it both ways just to make sure that everyone sees it the way that they're used to seeing it. Okay, so using the point slope form, I am going to use the x1, y1 that I already have labeled here, since nice and convenient. And y1 is 1, the slope is 5/4, and x1 is a -3. Okay, so subtract the negative is addition. And so now from here, what I'm going to do is I'm going to add 1 to both sides. And that's y. And then I'm going to go ahead and distribute here. So if we distribute, then that's going to be 5/4 x plus 15 over 4 plus 1. And of course, 1, which is the same as 1 over 1, we need to be able to add these together, so we need to have a common denominator. And that common denominator between 4 and 1 is 4. So to change 1 over 1 to something over 4, we would multiply numerator and denominator by 4. And we would end up with 15 over 4 plus 4 over 4. And thus, now that we have fractions with like denominators, we just add the numerators. 15 plus 4 is 19 divided by 4, and there is your answer. And so this is what the equation of the line is that goes through these 2 points. Okay. If we took the approach of doing the slope-intercept form, then we just pick one of these points, x1, y1 again. Doesn't matter. We can pick either one. We just need to plug in something for x here, plug in something for y, and plug in m. So to keep consistent with what I've done here, I'm going to use the point -3, 1 again. So for y, which is the same as y1, that would be 1 there. We know for the slope, that's 5/4. And of course for x, that would be a -3 there. So get rid of that, -3 plus b. Okay. And so now in this instance, we know that 5/4 times a -3, which is the same as -3 over 4, 1 will be a -15 over 4 plus b. Now, if you are the type that you don't want to deal with fractions, then the best thing you can do right now is to multiply both sides by 4. And you're doing that so that you can clear out your fractions. So I'm going to take that approach here. And so here we know that 4 times 1 is 4. And over this way, we're going to distribute to both terms. And so if we take 4 and multiply it times a -15 over 4, that's going to be the same as saying -15 times 4 over 4 plus 4 times b is just 4b. And notice that these 4's right here will reduce to 1, which will just leave you with a -15 plus 4b. And so now from there, we just need to solve for b. So we add 15 to both sides. And that will give us 19 equals 4b. And of course, we just divide both sides by 4. And we see that that will reduce to 1. And we have b is 19 over 4. So we know that our slope is 5/4. And our y-intercept, or our b here, is 19/4. And so now you see why this would actually end up being the answer here. So you just plug it in. Y equals m, which is 5/4, x plus b, which is 19/4. And you see that we get the same answer there. So this is how we actually approach problem number 6. Let's move on to number 7. So problem number 7 is another word problem, and we're asked to assume that what we're talking about in this word problem describes a linear relationship. So what that means to us is that we're basically going to be using something of the form y equals mx plus b to model this problem. So it says in a certain city, the cost of a taxi ride is computed as follows. There is a fixed charge of $2.45 as soon as you get into the taxi, to which a charge of $2.35 per mile is added. The first thing that we're asked to do is find an equation that can be used to determine the cost of an X mile ride. In other words, a 2-mile ride, a 5-mile ride, an 8-mile ride. And so instead of just saying a particular number, we're just saying X mile taxi ride. And then we want to use this equation to find the cost of a 3-mile taxi ride. Now, one thing I do want to say here is that I know most of you, by using common sense, you'll be able to sort of figure this out. What this question is actually testing is to see whether you can come up with the equation first and then use the equation, not just get the answer, okay? Because the thing is if we set this up differently, if we set up the cost rate a little differently, would you be able to model that correctly, okay? Now, whenever we talk about cost, we have what's called variable cost, and we have fixed cost. Okay, the variable cost is the cost of how many miles we're charged, the rate per mile that we're charged after we get into the taxi. The fixed cost is what we're charged as soon as we get into the taxi. So in other words, if the taxi person is, if you wave at them or whatever and they stop, just because they stopped and allows you to get into the taxi, you're being charged $2.45 there, okay? So we know everything's going to be in terms of x, so we're going to let our cost function equal c of x. Our variable cost is going to be $2.35 per mile, so that's going to be $2.35 times x. And then we're going to add to that the fixed charge of $2.45. Okay, so that's the fixed cost plus variable cost. So this is the first part of what I'm trying to test you on in this question. Can you come up with this? The second part is, can you use this to be able to come up with the amount that you're going to have to pay for a 3-mile taxi ride, okay? And so we simply just plug in 3 for x, since x represents number of miles. And so just plug this in to $2.35 times 3 plus $2.45, okay? And so once we're done with all that, we see that the $2.35 times 3, that part will end up being $7.05, plus the $2.45 will end up with $9.50, okay? And so that is what the taxi ride would be. So 3-mile taxi ride is $9.50. And let me make my currency unit there look a little better. And so that is how you do problem number 7. Let's move on to number 8 now. Okay, so for problem number 8, we're asked to solve this compound inequality, write the compound inequality in interval notation, and then express the answer on a number line. So we're asked to do 3 different things here. And so we're going to take care of the first things first, which is we're going to solve the compound inequality. So to solve this, the first thing that we need to do is distribute 2 to both terms here. So that'll be 2x minus 10. And then we need to add 10 to both sides. That cancels to 0. 6 plus 10 is 16, and 2 plus 10 is 12. And then to get x by itself, we just divide both sides by 2. And so 12 divided by 2 is 6. 2x divided by 2 is just x. And 16 divided by 2 is 8. So this is what the answer is in the inequality notation. We need to write it in interval notation. And so this tells us that x can be any number in between 6 and 8, including 6 and 8 itself. So how we write that in interval notation form is like this, where we use the brackets. And so if you remember, brackets mean that we include the n values, and parentheses means that we do not include the n values. Okay. Now, as far as how you're going to graph your actual solution set, there are several different ways you can do this. When I worked it out, I had all these things nice and numbered, and I think I had 6 here and 8 there, and I kind of did the brackets there. It really doesn't matter. Just as long as you sort of identify where 6 is, where 8 is, and you do your brackets. So I'm going to do this a little different than how I actually did it when I worked it out. So what I'm just going to say is let this be 6 here. I'm going to act like this is 6.5, 7, 7.5, 8. And then I'm going to do my bracket here, my bracket there, and then everything that is in between. And that would be what it would look like if I actually graphed the solution set. Okay. So as long as I see where you have 6, 8, some space in between, and you have your brackets, and you have everything shaded in, that's all I really need to see there. So that's problem number 8. Let's move to number 9. All right, so problem number 9 asks us to write this number in scientific notation. And so for us to remember here, we know that scientific notation looks like this, where it's a times 10 raised to some integer here. And of course, a is understood to be a number that is going to be in between 1 and 9.99. So we can say that. So basically, anything that's in between, including 1 all the way up to 10. That's essentially what I'm trying to say here. So we know that in, let's say, its raw form, let's say I'll just pick a number like 0.01, okay? So in its raw form, this is like 1/100ths times 10 raised to the 0, because we know anything raised to the 0 is 1. However, whenever I move the decimal to the right 1 space, that is making our exponent here more negative. And of course, if we move it again, then it's going to make it even more negative. So if I actually took this and I moved it to the right, it would be 1.0 times 10 to the negative 2, okay? Now, if I came and actually did it the other way, let's say if I had 1 times 10 raised to the 0, and let's say I wanted to move it in another direction, okay? So let's say if I took this and I moved it to the left, okay, then I would get more positive in that direction, okay? So essentially, what I'm trying to say here, since this is a small number and we're trying to make it into a bigger number to get into scientific notation, we have to go to the right, which makes our exponent more negative. If we're doing the opposite, which is, and I'll just kind of put it back into this form here of 1.0 times 10 to the negative 2, and we wanted to move back in this direction, now our exponent gets more positive, okay? And so for here, we know that we have to be a number in between basically 1 and 10, not including 10. So we need to move this decimal 1, 2, 3, 4, 5, 6 spaces over. Because when we move it there, the number that we end up having is 6.7415. And so since we move 6 spaces over to the right, we know that makes our exponent get more negative. That would have to be -6 there. So 6.7415 times 10 raised to the -6. Okay, so that is how we answer number 9. I'll go ahead and erase some of this and we'll talk about number 10. All right, so for number 10, we're asked to solve this system of equations here, and these are systems of linear equations by either substitution or elimination. And so it doesn't matter which method you use as long as you use one of them. And so we want to clearly indicate whether your solution is a single point, infinitely many solutions, or no solutions. So the first thing that we want to do here is if we were trying to solve this by, let's say, elimination, because I think this is an easier way to do it for this problem. We're trying to either eliminate our x variable or our y variable. Now, if we look at this, we'll see that if I look right here, if I had a -5 right there, and I added these two equations together, I would be able to eliminate x because -5x plus x is 0, okay? Now to do that, that would require me having to multiply both sides of the equation by a -5 because I just can't put a -5 there and just leave everything else alone, okay? So that's one way that we could approach this problem. Another way that we could approach this problem is realizing that we have a -7y and a -7y here. If I could make this a plus 7y and then add these equations together, then I would eliminate y because 7y minus y is 0. And that would actually be easier than multiplying the top equation by 5 on -5 on both sides. I can just multiply both equations by a -1 to create that plus there. So that's the approach that I'm going to use to solve this by doing elimination. So to do this, I'll just rewrite this and say -1 times x minus 7y equals -1 times 15. And then the second equation will stay the same. And of course, when we do this, all it does for the first equation is going to change the signs of each term. We have 5x minus 7y equals 19. And now from here, if we add these equations together, and we're adding them because we know that's one of the 3 rules that we can do whenever we are dealing with systems of linear equations here. We know that cancels to 0. A -x plus 5x is a positive 4x, and -15 plus 19 is a positive 4. And then from here, we can just divide both sides by 4. And of course, 4 divided by 4 is 1. 1 times x is x, and 4 divided by 4 is 1. So we know what x is now. So from there, all we have to do is plug in x into one of our 2 equations. I would probably take the first one, plug that in for x, figure out what y is. So therefore, plug in 1 for x, minus 7y equals 15. I'll subtract 1 from both sides. That cancels to 0. 15 minus 1 is 14. And if we divide both sides by -7, that will give us y equals -2. So we know our answer here is the point 1, -2. And what this actually means is if we call this equation 1 and equation 2, we have one equation, which is equation 1 going like that, and we have another equation, equation 2, going like that. And at this point right here is where they intersect, and that point would be the point 1, -2. So that is actually what it means whenever you solve this system of linear equations. And so the way that I've done it here is by the elimination method. So I'm going to erase this and now do it by the substitution method so that you see how it actually works that way. Okay, so if we want to solve this same system of equations by the substitution method, then we need to either write x in terms of y or y in terms of x. Probably the simplest way to do this is to take equation 1 again and rewrite it as x equals whatever, okay? So let's take this and add 7y to both sides. Of course, that cancels to 0. And since 15 and 7y are unlike terms, then the most we can do is just rewrite it as 7y plus 15. So we take that, and then from here, we're going to take this equation that we just came up with, which is just basically equation 1 rewritten, and we're going to substitute everything that we see here for x in here. So 5x minus 7y equals 19 is the same as 5 times 7y plus 15 minus 7y equals 19. And of course, from here, we know at the 5, we're going to distribute that to both terms there. So 5 times 7y is 35y. And we know that 5 times 15 here would end up being 75 minus 7y equals 19. And so from there, 35y and minus 7y are like terms, so we're going to combine those. So 35 minus 7 is 28, so that'd be 28y plus 75 equals 19. And so from there, we will just subtract 75 from both sides. Okay, so we know that 75 minus 75 cancels to 0. We have a 28y here, and 19 minus 75 will give us a minus 56. Carrying on here, I'll just go ahead and rewrite this. We know that if we divide both sides by 28 so that we can get y by itself there, we know that that would reduce to 1, and negative 56 divided by 28 is a negative 2, because we know that 28 times 2 is just 56. So of course now we know what our y is. So now that we know what y is, of course we can come back up here and plug that y into here to figure out what x is. And so we plug in y. See that that is a negative 14 plus 15, which gives us a positive 1. And so just like how we had before, we see that x is equal to 1, y is equal to negative 2. And so to make sure that you get full credit for this problem, you need to make sure that not only do you find out what x and y are, but that you actually put it in an ordered pair if you actually have an answer like that. If you have infinitely many solutions as an answer to the problem that you're working on, then you'll know that because you'll have a 0 equals 0 whenever you do all of this. And all you need to put there is just infinitely many solutions. If you end up with something that looks like 0 equals, let's say, negative 9, then you will know that that is no solution. And so once you see this, you just write no solution. So although this problem doesn't go over the cases of infinitely many and no solution, if your problem should happen to be that in doing either one of these methods, you will see 0 equals 0 in the infinitely many solutions case, or two numbers not equaling each other that you know aren't equal to each other in the no solution case. And then once you see that, you just need to state either infinitely many solutions or no solutions respectively. Okay. All right, so we'll go ahead and move on to number 11 now. Okay, so for number 11, we're asked to take this rational expression here and that has things with exponents in it and to basically simplify it. And so we're having to remember a lot of different rules here. So please remember that there are several ways to do this particular problem. I'm just going to do it the one way that actually makes sense to me right now. okay? And so the first thing I'm going to do is try to simplify everything that I see inside of the parenthesis first before dealing with this negative exponent, okay? So in dealing with that, I know that I have x over x to the fourth times y cubed over y, all that raised to the negative 2, okay? So here I know that x divided by x raised to the fourth means I have 1x on top in the numerator, 4 x's multiplied by each other in the denominator. And so if I wrote that out, it would actually look like this. And so here we know that a pair of these x's will reduce to 1, and all we have left is 1 over x times x times x, which is just 1 over x cubed. So that is what that part would simplify to be. For the y cubed divided by y, of course I got y times y times y over y, and of course a pair of those are going to reduce to 1, and all I have left is y squared over 1. Okay, so have that raised to the negative 2. Now, if I multiply this fraction times that fraction, I end up with y2 divided by x cubed, and all that raised to the negative 2. And so that's the first part. The other part of this is to remember that whenever we have something raised to an exponent, we could raise the numerator by that exponent and the denominator by that exponent, okay? And in doing that, what we would end up with is this. We would have y squared, all that raised to the negative 2, over x cubed, all that raised to the negative 2. So from that point, we also realize that anytime we have an exponential number or expression raised to another exponent, like how we see here, we can multiply the exponents. So that means here this would be y raised to the negative 4, because 2 times a negative 2 is a negative 4. X raised to the negative 6, because positive 3 times negative 2 is a negative 6. And so now from here, there's several different ways you could approach doing this. And the way that I'm going to approach it is to say that when I have y raised to the negative 1/4, I could rewrite that as 1 over y to the positive 4. And same deal here. X raised to the negative 6 is 1 over x raised to the positive 6. And if you notice here, I have a complex fraction. And so with complex fractions, we do keep, change, flip. And so we keep the first fraction the same. We change the operation from division to multiplication, and we flip or take the reciprocal of the bottom fraction. And so now from here, we just multiply everything together. So 1 times x raised to the 6 is just x raised to the 6, and y raised to the 4th times 1 is just y raised to the 4th. And that is your answer, okay? So that's one way to do this problem. Now, if that was a little bit too complicated for you, at this stage right here, before I drop off to the second line, I'm actually going to do this a different way, and maybe that way would actually be a little bit better for you. So give me a second to erase this bottom line here, and I'll rework this another way if that way didn't sit well with you. All right, so at this point, if the other way I worked did not work well for you, I'm going to do this another way from this point. And so now from here, another way that we can do this is we could go ahead and realize that anytime we have something raised to a negative exponent, it's the same as saying 1 over that same thing raised to a positive exponent. So here what I could do is I could rewrite what I see here as 1 over y squared over x cubed, all of that raised to the positive 2. And so now, like how we talked about last time, here we can use this rule here, which says that the quotient of two things raised to the same exponent, we can raise the numerator and denominator to that exponent. And we could also use the fact that any exponential number raised to another exponent means that we multiply the exponents by essentially coming up with this as a result. So y squared would be y to the fourth, and x cubed squared, or x cubed raised to the 2, is just x to the 6. And so now we have this situation. So from here, whenever we have 1 over anything, it is asking us for the reciprocal, okay? Since we have a fraction here, we know that 1 over the reciprocal is just taking what's in the bottom and flipping it. So we could say that's x raised to the 6 divided by y raised to the 4. And so by definition of reciprocal, we could answer that a bit easier instead of having to do the whole keep change flip thing, okay? So I hope one of those ways of doing it actually helped you out. Let's move on to number 12. All right, so for number 12, we're asked to multiply the following polynomials by using the FOIL method, vertical stack method, or box method. So I'm going to do all three just to make sure that everyone sees their way that they like to do it, okay? And the first way I'm just going to do it is by the regular FOIL method, or just distributing, okay? So I'm going to first multiply 9x times x squared, then do it by negative 5x, then do it by 1, and then turn around and multiply negative 1 by x squared, then by negative 5x, and then by positive 1. So when we do that, 9x times x squared will give me 9x cubed. 9x times a negative 5x will give me a negative 45x squared. And a 9x times 1 just gives me a plus 9x. So now what we do is we will multiply negative 1 by everything over here in the second factor. So negative 1 times x squared is a negative x squared. Negative 1 times a negative 5x is a positive 5x. And negative 1 times a positive 1 is a negative 1. And so now from there, all we need to do is combine like terms. So we know that negative 45x squared and negative x squared combine to be a negative 46x squared. 9x cubed, I wrote that here because there's nothing else that it can match up with. Here we see that positive 9x and positive 5x gives us a positive 14x. And then the only thing that's left there is a 1 or negative 1. And we just write that like that. So that is doing the distributive or FOIL method. Next, going to do it by the vertical stack method, if you like to do it that way. So I'm going to erase and then write this over. All right, so I've written the answer that we got last time up at the top just to make sure that we keep up with that. And if we want to do this by the vertical stack method, then I would suggest that the one that has the most terms, you put that on top, and the one that has the least amount of terms, you put that on bottom. And so we're going to multiply this the exact same way we would multiply something like 231 times 12. We're going to multiply it the same way. Of course, for this problem, we would say 2 times 1 is 2, 2 times 3 is 6, 2 times 2 is 4. And then we would put an x here or a 0, and then just multiply 1 times 1, 1 times 3, 1 times 2, and that would give us this, add, and that would be our answer then. So we're going to do this problem the same exact way. So a negative 1 times a positive 1 is a negative 1. Negative 1 times a negative 5 is a positive 5x. Negative 1 times x squared is a negative x squared. And then here, we're going to put a plus 0 here, just like how we put 0 there. 9x times 1 is positive 9x. 9x times a negative 5x is a negative 45x squared. And then 9x times a positive x squared is a positive 9x cubed. And of course, we just add all that together. And we see that when we do that, we get the same thing as we got last time. Okay. Now I'm going to erase this one more time, and we're going to do this by the box method for those of you that work it out that way. All right, so if you do this by the box method, then one of the things that you're probably wondering is, how do I actually set up my boxes correctly? And so to me, you have to look at the number of terms in each factor to determine whether the dimensions of your box is going to be. So here you have 2 terms and here you have 3 terms. So if I were doing this, I would create a box that's going to be a 3-row, 2-column box. And so I would basically list x squared, x squared here, minus 5x there, plus 1 there, a 9x here, and a minus 1 there. And I would make my box according to that. Okay. And so now within the box, we see we're going in every intersection. So we're saying x squared times 9x is 9x cubed. X squared times a negative 1 is a negative x squared. Negative 5x times a positive 9x is a negative 45x squared. Negative 5x times a negative 1 is a positive 5x. And 1 times 9x is 9x. Try to fit it in here. And 1 times negative 1 is a negative 1. Okay? So from that point, we move in diagonals to add everything up. So, of course, here, this ends up being a 9x cubed. Well, let me not write it there. It will be better off here. So this equals 9x cubed here. And if we go in diagonal this way, negative 45x squared plus a negative 1x squared is a negative 46x squared. 9x in diagonal plus 5x is a positive 14x. And of course, negative 1 is by itself. So depending on whether you do it the FOIL method or the distributive method, vertical stack method, or the box method, either way you should get the same answer. So let's move on to number 13 now. All right, so for our next problem, we're asked to factor this trinomial completely. And again, we're calling this a trinomial because this is a polynomial with 3 terms. So before we begin here, there's a few things that we want to look at before we start. The first thing that we want to see is, which I call the low-hanging fruit. We see that we have an x raised to the 5, x raised to the 4, and x raised to the 3. Since x raised to the 5 is basically 5 x's multiplied times each other, and x raised to the 4 is 4 x's multiplied times each other, both of those have at least x cubed, or x multiplied times itself 3 times. So we know that a common factor that each of these have is x cubed. So we could rewrite this as 4x cubed times x squared plus 24x cubed times x minus 108x cubed. Okay, and we see that each of these have a factor of x cubed. The next thing that we want to see here is that 4 and 24 both have a common factor of 4. And we know that because 4 times 6 is 24. Okay. Now, if we're looking to see, all right, well, will 108 also have a common factor of 4? You may not know that directly, but we can figure it out right quick. So let's take 4 and divide it. 108 and divided by 4. So we know 4 goes into 10 2 times, and 2 times 4 is 8. 2 remainder, bring down the 8, And we know 4 goes into 28 7 times because we know 7 times 4 is 28. So yes, it does work. So here we know that this will be 4 times x cubed times x squared plus 4 times 6 times x cubed times x. And let's get that looking a little better there. Minus, and now we know that 4 times 27 is 108 times x cubed. And let's get that looking a little better. Okay, and we'll section that off. So now, from what we see here, we have a 4 that is in common with all terms, and we see we have an x cubed that is in common with all terms. So let's go ahead and factor out a 4x cubed out of all terms. So if we factor out a 4x cubed, what is left in the first term here is just x squared. What is left in the second term here, after we factor out a 4 and the x cubed, is just 6 and x, so plus 6x. And then after we factor out the 4 and the x cubed, all we have here is minus 27. Okay? So what we've just done here is factored out the greatest common factor out of each of these terms. So what we're going to do now is see with this other factor here, x squared plus 6x minus 27, can we actually factor that into two binomials? Now, in factoring binomials, if we look at the trial and error method, the first thing that we learned is that if we know that our leading term here of our trinomial has a leading coefficient of 1, meaning that there's not 1 there, and because of how these signs are, we know that in the factoring, we're going to have x here and x there, and since this is plus minus, one of these is going to have to be minus, one of these is going to have to be plus. And so from that standpoint, we look to see here what numbers multiply to be a negative 27, but add to be a positive 6. And if we go through our multiplication tables quickly, we'll quickly find out that 9 times 3 is 27. So if we wanted this to be a negative, but have the sum of this number and that number end up being positive, then we would need to make the 3 negative here and the 9 positive in order to get a negative 27. And so what that means here is that 9 must be here and 3 must be there. And so, of course, to check this out, we can always check the two middle terms here. X times 9 is 9x, and negative 3 times x is a negative 3x, and that equals positive 6x, so we're good. And so this will actually be our answer here. And so this answer means that we have factored this particular trinomial completely. Let's move on to number 14. All right, so for number 14, we're dealing with radical expressions now. And so what we want to do is try to simplify these as much as possible by adding, or in this case, subtracting. And so the key to this is to understand that in order to be able to add these together, we're going to have to rewrite these in such a way to where we're going to have some like terms, okay? So we realize here that we have 8 times the 4th root of x raised to the 7th. And we also see that we have a 4th root of x raised to the 3. If we took 4th root of x raised to the 7, we realize that we could really rewrite it like this. Because we know x raised to the 3 times x raised to the 4 is x raised to the 7. And we also know from our rules about radicals that we could rewrite it this way. Okay. So in that, we see that in the fourth root of x raised to the seventh, there is a fourth root of x cubed in there. So these two terms, even though they don't look like it, they are like terms, okay? Another thing is that, do you see how we have the fourth root of x raised to the fourth? Now, essentially what this is doing whenever we do the fourth root of x raised to the fourth, we are basically reversing the operation of raising something to the fourth. Simply put, we just get x here. But how that actually happens is if we translate this back into its fractional exponent form, and I'm referring to this, by the way. Let me use a different variable here. So if we have the nth root of x raised to the m, then we know that we could rewrite it as x raised to the fractional exponent m divided by n. So if we did this here, that would be x raised to the 4 divided by 4. And of course, here we would keep this the same, but we know that x raised to the 4 divided by 4 is just x raised to the 1, and anything raised to the 1 is just itself. And so we would rewrite it that way. So whenever we write out this part of the problem, we know that it will be 8 times all of this here, okay? So we're going to go ahead and do that now so you can see what that's going to look like. So we have 8 times fourth root of x raised to the 7th minus 4x fourth root of x cubed. And so here, we're going to say 8 times fourth root of x cubed times fourth root of x raised to the 4. And we'll rewrite this other part. Erase that, make that look a little better. And so now we know from what I've explained over here that this fourth root of x raised to the 4th, all that is just equal to x. So that'll be 8 times x times fourth root of x cubed minus 4x fourth root of x cubed. And so now at this point, we see that we have like terms here because both of these have a fourth root of x cubed. And so all we need to do now is we treat this just like this was like 8xa minus 4xa. And so 8x minus 4x gives us a positive 4x times fourth root of x cubed. And so this would be your final answer. So now we'll go ahead and move on to number 15. So for number 15, we realize that this is a rational equation. And so in dealing with rational equations, there's two things that we want to do before we get started. The first thing that we want to do is we want to figure out what solutions we know we can't have before we begin. And the second thing that we want to do is we want to find out what our LCD is going to be. And we're wanting to do that because we're wanting to use our LCD to be able to multiply both sides of the equation by it so that we can get rid of our quote-unquote fractions, okay? So the first thing that we should do before we even get started here is, since we know that y plus 5 and y minus 5 are prime denominators, meaning that there's nothing else that we could divide this by except for 1 in itself, we need to factor out what y squared minus 25 is. So I'll rewrite this equation here. We know that y squared minus 25 factors out to y plus 5 times y minus 5, okay? And so from here, we see that if we plugged in a negative 5 here, we would get 0 in the denominator which is something that we know we can't have. So we know y is not allowed to equal to -5. If we plugged in 5 here, then we see that 5 minus 5 is 0 in the denominator, and we can't have that either. And of course here, -5 would make the whole denominator 0, 5 would make the whole denominator 0. So we know that the answers that we know we cannot have are -5 and 5. So when we do this process, if we know that -5 and or 5 ends up being one of our solutions, then we know that we're going to have to throw that solution out. And that's what is called an extraneous solution, okay? And I'll spell that word just in case you may not know what it is. So extraneous, okay? Also, the other thing that we need to find out is what is our LCD. And so since we have our rational expression on the right side of the equation already factored out, we can easily see that the LCD should just be y plus 5 times y minus 5, okay? Now, if you did not know that, the process for figuring it out, regardless of what you have, is as follows. So notice that we have y plus 5, y minus 5, and we have y squared minus 25. Since y plus 5 and y minus 5 are prime, we just rewrite those. Kind of like if we had 2 and 3 here, then 2 is a prime number, so we just write 2. 3 is a prime number, so we just write 3. And what we're doing here is we're factoring these expressions into what's called their unique prime factorization. For y squared minus 25, we know that that factors to y plus 5 times y minus 5. And so just like how we do for regular numbers, we know that we have y plus 5, y minus 5 as the two prime or unique prime factors in all of these. So we circle the row that has the most amount of y plus 5s and the row that has the most amount of y minus 5s. Since we see that y plus 5 only shows up once here or here, we can just circle one of them. So I'll circle this one. Y minus 5 shows up here and here, and so since both only show up once in each row, we'll just circle this one. Everything that I've circled is what we multiply, and that is what our LCD is going to be. And so that's how we know that y plus 5 times y minus 5 is our LCD, okay? So I'm going to rewrite this here. LCD is y plus 5 times y minus 5. And I'm going to make some more room for us so that we can actually start doing this problem now. Okay, so now that we have figured out what we know, what we can't have for solutions and what our LCD is, we're going to multiply both sides by this equation, by the LCD, in order to get rid of the fractions now. So I'm going to say y plus 5 times y minus 5, and all that times 7 over y plus 5 minus 5 over y minus 5, and that's going to be equal to 12 over y plus 5 times y minus 5, and all of that is multiplied by y plus 5 times y minus 5 on the right side, okay? When we distribute this to both terms, when we do the first one here, I'm going to write this out the long way just to make sure that you can see it. So when we multiply all this together, remember that this is the same as this over 1. So we will have 7 times y plus 5 times y minus 5 all over y plus 5, okay? Minus 5 times y plus 5 times y minus 5 all over y minus 5. And of course, on the right side, we just have 12 times y plus 5 times y minus 5 all over y plus 5 times y minus 5. And so at this point, you see that we have the two y plus 5s that are in common, so we can reduce these common factors to 1. And let me move that back. Mess that up there. Let's try again. So Come here and move those common factors to 1. And that will just give us 7 times y minus 5. Here we have y minus 5 here that are common factors, so we're going to reduce those to 1. And we just have 5 times y plus 5. And here, that and that reduces to 1, and y minus 5 reduces to 1. So we just have 12. And so from this point, we see that we just have a linear equation and we just need to solve it. So we need to take our 7 and distribute to both terms there. Negative 5, distribute to both terms there. When we do that, we get 7y minus 35 minus 5y minus 25 equals 12. And so if we combine like terms here, we see that 7y minus 5y gives us a positive 2y. And we'll see that negative 35 minus 25y will give us a minus 60. And that will give us equal 12. Okay, so from that point, keep on going. If we have 2y minus 60 equals 12, if we add 60 to both sides, that cancels to 0. 2y is equal to 72. And we divide both sides by 2 here, and we'll see that y ends up being 36. And so since 36 does not match negative 5 or 5, we know that given that we've done everything else right, that this actually is the solution. Okay, so your answer here will be y equals 36. So let's move on to number 16 now. So for number 16, we have an expression that has an irrational expression in the denominator, and what we want to do is rewrite this expression in order that the denominator is rationalized. And so how we do that is we know that for any irrational expression here of the form, we'll just say a minus b. Oops, sorry. Should just be a minus b like that. Let me just write it all over. A minus b. If we multiply that expression by its conjugate, which is a plus b, then this answer would end up being a squared minus b squared, in which this ends up being a rational number. And if you remember, a rational number is a number that can be written as a fraction. So numbers like 1, negative 2, 1.5, 6.56, 56, 56, 56, repeat, or 1.33333, repeat. Okay. Now here, since we have 9 minus square root of 5, what we want to do is multiply numerator and denominator by 9 plus square root of 5. And so where the 9 is representing a here and the square root of 5 is representing b. In the denominator, we know that that's just going to be 9 squared minus square root of 5 squared. In the numerator, we're going to take 7 and distribute it to both terms here. So 7 times 9 is 63, and 7 times square root of 5 is just 7 times square root of 5. There's not much else we can do to that. In the denominator here, we know that 9 squared is 81, and square root of 5 squared is, it's like taking square root of 5 and multiplying it times itself, which is the same as square root of 25, which is just the same as 5. So we say that minus 5. And of course, 63 plus 7 times square root of 5 there. And of course, to finish this up, we know that 81 minus 5 is just 76. We just do 63 plus 7 times square root of 5. So 63 plus 7 times square root of 5 all over 76 is how we would leave this answer here. So let's move on to number 17. All right, so for number 17, first thing what we see here is that we need to solve this radical equation. And so we don't focus on graphing a whole lot in this particular course. So what we want to do here is at least give us some kind of checks and balances to have us make sure that whatever answer we get, it actually makes sense. We're going to solve the problem, but we're also going to use some insight before we do it. Now, what I'm about to do is something that you don't necessarily have to do. This is just something just to give you a sanity check. If you remember, when we talk about the domain of a function, because remember, we're thinking about this whole equation here as asking us a graphical question about a function. And so our function here is square root of 4x plus 7, all that minus 9, okay? And so what we're really asking here is, does this function have an x-intercept? And one of the things that we know is that for the domain of this function, we know that any expression that is under the radical here must be greater than or equal to 0. So if we set that greater than or equal to 0 and then solve for x, like how I'm doing here, what we see is that whatever answer that we get for x is going to have to be greater than or equal to -7/4, okay? And so that's like -1.75. So whatever answer that we get here, it should be a number that is -1.75 or larger, okay? Now, with that being said, the other thing that we're going to do here is go through the process of solving this as normal, and then we're going to check our answer, okay? So here to start us off, and I'll just come down here and write this. We know that in order to solve for x here, we have to get rid of the square root sign. And so the only way that we're going to be able to do that is to have is to be able to square both sides. But to do that effectively, we need to have everything that just has a square root in it on one side and everything else on the other. So how we're going to accomplish that is by adding 9 to both sides. And so that cancels, we get 9 over here, and we have 4x plus 7 all under the square root sign there. So from this point, we know that we can square both sides, and when we do that, this will effectively undo the square root sign and just give us the 4x plus 7, and we would have equals 9 squared, which is 81. And so from there, we just solve this equation. So subtract 7 from both sides, and so now if we do 81 minus 7, that should give us a 74. That didn't work out too well. And then let's divide both sides by 4, okay? So from there, we would have just x on this side. And of course, 74 divided by 4, we know that if we try to actually do that manually, let's see, 4 goes into 7 once with a remainder of 3. And so 4 goes into 34. That would be, what, 8 times with a remainder of 2, so like 18 and a half. So we know it's not going to go through cleanly. So this, we can just do it this way. So we know that 2 goes into 74 3 times, so it'll be 37. So 2 will go into 4 2 times, and 2 will go into 74 37 times. So that would give us 37 divided by 2, which is the same as 18 and 1/2. So you can either do it like that, or you could say this is 18.5. Either way is fine. So from here, what we want to do is plug in our answer here to make sure that we are correct. And so I'm going to use the fraction version of our answer because it's actually easier to check that out. So we're going to make some room over here and check our answer. And so after I'm done checking the answer, I'm actually going to graph for you what this looks like and show you why the answer that we have is either correct or incorrect. Okay. All right, so in checking our answer here, we're going to say square root of 4 times 37 divided by 2 plus 7, all that minus 9 equals 0, and we want to check to see if that is actually going to, the left side is going to equal the right side. So here we know that 4 times 37 over 2, we know that this 4 is like 4 over 1, so we can reduce 4 and 2 here to just 2. So 2 goes into 4 2 times, 2 goes into 2 once, and of course 2 times 37 is just a 74 plus 7 minus 9 equals 0, question mark. And 74 plus 7 is 81 minus 9 equals 0. Square root of 81 is 9. And of course, 9 minus 9 is 0. So it checks out. Now, what this actual graph looks like, for those of you that are interested in knowing that, is this would look something like this. And I'm going to clear a little room here so that you can kind of see what I'm talking about. Let's get rid of that. All right, so here we know that the domain of this is going to be all values of 7/4 or larger. And here what this would be saying is that if this was the x-axis, that was the y-axis, that I have some variation of a theme of square root of x, which is a graph that kind of looks like this. It's going to start at the point negative 7/4, negative 9, which would be here. And it's going to go like that. And of course, literally what we're saying here is that whenever we solve this equation, we're asking when does that particular function have an x-intercept? Or where does it cross the x-axis? We see that that happens at about right here. And for us, we found out that that answer was 37 over 2, or 18.5. And so from that, we knew that we had to have one answer. And whatever that answer was, it has to be greater than or equal to negative 7/4, or negative 1.75. So in this course, we don't go over how to graph that. But if you have a graphing calculator, you could actually put this square root of 4x plus 7, all that minus 9, into your calculator and see this particular graph. And you'll see that it actually crosses the x-axis at 37 over 2. And that is what this question is actually asking us to find out without actually drawing the graph to do it. All right, let's move on to number 18. All right, so question number 18 is asking us to solve this quadratic equation by using the quadratic formula. And so this is a formula that you definitely need to remember. And I'm going to write it here. So this x sub 1, 2 just means that we're expecting up to 2 answers. And the quadratic formula is just minus b plus or minus square root of b squared minus 4ac. All of that over 2a, where our a, b, and c come from our quadratic equation in this form. And so you can see from here that our a should be 2, our b should be 10, and our c should be 5. Let's make that equal sign look a little better. And so all we have to do here is plug in a, b, and c into our quadratic formula here and figure out what the answer is. What I'm going to do first is I'm going to calculate this b squared minus 4ac expression under the square root, which is called the discriminant. And so the reason why I'm wanting to do that first is the discriminant actually tells us what type of solutions we expect to get. And so I'm going to quickly review that before we actually go through the computation for the problem. When b squared minus 4ac is greater than 0, we know that we have two distinct real number solutions. And so what that means for us graphically is if we were trying to graph what this equation is asking us, is basically saying that we have two x-intercepts, okay? And this would be x1, that would be x2, okay? So all quadratic equations are modeling quadratic functions, which basically look like u's or parabolas. And when we have b squared minus 4ac being greater than 0, we know that that particular graph crosses the x-axis at exactly two places. When b squared minus 4ac is equal to 0, then this is what's called a double root. And what this means is we just have one real number solution. And our graph would look something like this. And this is without loss of generality here. So this would be our x1, which is also equal to x2 there, okay? So we just have one answer that appears twice, and this is what that would mean. In the case of b squared minus 4ac being less than 0, then we would have two complex conjugate solutions, okay? And so complex conjugate solutions, what that's communicating to us is that our equation is of a parabola that kind of looks like this, where the parabola itself does not cross or touch the x-axis at all, at any time. And so whenever we know that we end up having basically negative numbers under a square root sign, we're talking about complex numbers at that point, okay? So we can tell from the discriminant what our solutions are going to look like before we even calculate them, okay? So I'm going to make some room and then actually go ahead and do the calculations. All right, so now that we've made sense of what the discriminant is, we're going to go ahead and calculate it now. So our b is 10, so we just take that, square it, minus 4a, which is 2, c, which is 5. 10 squared is 100, and 4 times 2 is 8, and 8 times 5 is 40. And so 100 minus 40 is 60. So we know that we're going to have two distinct real number solutions here, okay? So now we'll go ahead and type in our discriminant. We'll use our discriminant to figure out our answer. So we have a minus b, which is 10, plus or minus square root of, and we know that b squared minus 4ac is just 60. And we take that, divide that by 2 times a, which is 2. So here, that just gives us a negative 10 plus or minus. And here for square root of 60, we know that 60 can be broken down to many things. But one of the things that we do know is that 60 is the same as 4 times 15. So that means square root of 60 would be the same as square root of 4 times 15, or square root of 4 times square root of 15. So here we're going to rewrite this as square root of 4 times square root of 15. Now, the reason that we want to write it that way is because we want to rewrite 60 factored out in terms of perfect squares. If we were to break down 15 more, we know that 15 is just 5 times 3. And of course, 5 and 3 are both prime numbers. So whenever you do the square root of a prime number, you end up with something that's irrational. So needless to say, breaking down square root of 15 to square root of 5 times square root of 3 isn't going to help us any, okay? So, of course, our denominator 2 times 2 is 4. And so from here, we know that square root of 4 is just 2. And so we can rewrite this as negative 10 plus or minus 2 times square root of 15 all over 4. And so now from this point, we can either factor out a 2 out of both terms in the numerator and then reduce, or we can break this up into separate fractions. I am going to break it up into separate fractions. So if I do that, that will be a negative 10 over 4 plus or minus 2 square root of 15 over 4. And of course, 10 and 4 both have a common factor of 2. So 2 goes into 10 5 times, 2 goes into 4 2 times, plus or minus. 2 goes into 4 2 times, so this would just reduce to 1 over 2, so that would be square root of 15 over 2, like that, okay? And then of course, since both of these have the same denominator, you can bring these back together. Say plus or minus square root of 15 all over 2. And so this should be your final answer. All right, so we'll go ahead and move on to number 19 here. Oh, and one thing I want to add is you can either leave your answer like this, or you can separate them and make them separate answers like this if you like. So I will be fine with you either leaving it in plus or minus form like this or breaking them out separately. Either way is fine with me. All right, let's go ahead and move on to number 19. Okay, so for number 19, we're asked to graph this exponential function. And so just to make sure that you understand this correctly, this is not 3 times x. So I'm going to erase this here. It's 3 raised to the x. And what we learned from the videos I prepared for you about the exponential functions is that we know that any exponential function where its base is greater than 1 is going to have 3 key points. And those 3 points for the x coordinates are negative 1, 0, and 1. And for the y coordinates are 1 over a, 1, and a, respectively. So for here, since our a is equal to 3, then what that means for us here is that this is just going to be negative 1, 0, 1, 1/3, 1, and 3. And so we know that our exponential function, whenever it's increasing, which we know it is because a is greater than 1 here, we don't have a negative sign on our exponent, that our graph is just going to go up like this. If it was exponentially decreasing, then we would have something that looks more like this. I'll just use an example here. We would have something like 1/3 raised to the x, which we could rewrite this as 3 raised to the negative 1 raised to the x, or 3 raised to the negative x, and that graph would go like this. And the only thing that would change there is that 1/3 and 3, these two would switch places. So you would have negative 1/3, 0, 1, and 1 1/3 instead of what we have here, okay? So in relation to this problem though, we just need to graph these 3 ordered pairs here. So we have a negative 1, 1/3, which I'm going to estimate to be about right there. We have a 0, 1, which should be right here. And we have 1, 3. So 1 in the x direction, 1, 2, 3 up, should be about right there. And so all we're going to do now is just play connect the dots. And so another thing that we learned is that with any basic exponential function, we have horizontal asymptote at y equals 0. Okay? And of course, our graph cannot touch or cross this particular line here. So it's not going to touch or cross the x-axis. So I'm going to come here, kind of ride on top of it, go up, 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 up. And of course, I missed it by a little bit, but hey, as long as you get the general vicinity of it, it'll be fine. And of course, on this side, we'll come here, put some arrows there, and that's what the basic graph of 3 raised to the x looks like. Okay. All right, so let's move on to number 20 now. So number 20 is dealing with a logarithm. And so I'm going to actually put this in parentheses just to make sure that we know that what we're taking the logarithm of. From the videos that we reviewed, we know that logarithms are the inverse of exponentials. And so one of the things that we know here is that if we can rewrite what's on the inside of the logarithm in terms of powers, that we could simplify this logarithm without needing a calculator to do it. Okay? And so when I am grading your paper, I'm looking to see, are you actually going to show me the work? And you will get full credit if you show all the work. If you do not show all the work and just use your calculator, you will not get full credit for this problem. Okay? So I just want to make sure that you know that up front. All right, so let me section this off a bit here. And so we know that log of 1,000, which means log base 10 of 1,000, we know that 1,000 is 10 times 10 times 10, or 10 raised to the 3, okay? And so in knowing this, if I rewrote this like that, then one of the things that you learned in watching the logarithm videos is that anytime we have log base a of a raised to the x, our logarithm properties tells us that that is just equal to x, okay? So here we know that log base 10 of 10 raised to the 3 is just going to equal to 3. So that's one way we can actually do this problem, okay? Now, the other way that we can do it is we could use another property, in which this property is something like this. So if we have log base a of some exponential m raised to the p, then what we could do is move that p out like that and just say p times log base a of m. And so I'm going to erase this and show you how that would look if we did it that way. So if we did it that way, then here we would say, all right, I can move this 3 out in front and just say 3 times log base 10 of 10. And so we have another log property that says log base a of a is always equal to 1. And so here log base 10 of 10, all that is just equal to 1, and 3 times 1 is 3. So when you're doing this, whether you do it the first way or the way that I've done it here, that is what I'm actually looking for whenever you do this problem. And remember, if you just give me the answer without showing me any work, then you do not get full credit for the problem. Okay? All right, let's move on to number 21 now. All right, so number 21 is two rational expressions that are divided by each other. And what we want to do is try to find the quotient and simplify. Okay? So this is similar to another problem that we did earlier in our review here. And I'm actually going to go and find out which one it was so that you can actually look at it here. I believe it was like towards the beginning. Just give me a second here to find it. Yeah, it was like number 11. So similar to that, not the exact same, but using some of the same rules there, okay? So just like how we did in that problem, the first thing that I'm going to do is to do my best to simplify each factor first, okay? So, well, in this case, each quotient. So here I have 5 over 2 times x squared over x times n over n squared. Of course, that's all one quotient, divide by, and here I have 10 over 15 times x squared over x times n squared over n, okay? So now from there, of course, 5 and 2, there's not much we can do with that, but we know x squared over x just simplifies to just be x over 1, and n over n squared simplifies to be 1 over n. Divide by. Both 10 and 15 have a common factor of 5, so 5 goes into 10 2 times, 5 goes into 15 3 times, so we have 2/3 there. X squared divided by x is just x over 1, and n squared divided by n is just n over 1. And so now if we take all these things inside each of the parentheses and multiply them together, we have 5x over 2n divided by 2xn divided by 3. And now, since we have we have a complex fraction here, or a fraction divided by a fraction, we can now apply the rule of keep, change, flip. So we keep the first fraction the same, we change the operation from division to multiplication, and we flip or take the reciprocal of the bottom fraction, okay? And so then from there, if you notice, we have an x up here and an x down there, and so those two x's, if we multiplied everything together, which like how I'm going to do here, 15x over 4x times n squared, because n times n is n squared, we see that these two x's can be reduced to 1. And so our final answer here is just 15 over 4n squared. Okay? And so that is how we do number 21. All right, and so now we are finally at our last problem, number 22. So let's go ahead and go over that. All right, so for our logarithmic expression that we're given, we want to rewrite this as a sum or difference of multiples of logarithms, okay? And so just to be clear here, we know that logarithms are just fancy ways of expressing the exponent of an exponential function, okay? So we're wanting to use some rules that we know from the exponential expressions written in reverse. And so one of the rules that we know of that we're going to start off using is the rule that whenever we have log of some base of, let's say, x divided by y, then that is the same thing as saying log base a of x minus log base a of y. And where this rule actually comes from is it is the same rule that we use, excuse me, to say that if we have, let's say, a raised to the x divided by a raised to the y, that we could basically subtract the exponents. And so here you see how these logarithms are being subtracted there, okay? And that's one of the reasons why I'm saying a logarithm is just a fancy way of expressing the exponent of an exponential function here. Because you see we're subtracting logarithms, which is like subtracting exponents, same thing as we see here. And if we look here, we got the division going on just like how it's going on there. So just trying to give you some background as to why this actually is what it is. But we're going to rewrite this as log base 2 of x raised to the 4th minus log base 2 of y raised to the 7th, okay? Now, the other rule that we're going to use is one I mentioned in problem number 21, which is whenever we have log of some base raised to, well, log of some base evaluated at some exponent, so in other words, something raised, well, m raised to the p here, then we could take this p and move it outside of the logarithm and rewrite it like this. Log p times log base a of m in this case, okay? So for here, since we have a 4 in the exponent there, we can pull that out and we can rewrite this as 4 times log base 2 of x minus, take that 7, pull it out, 7 times log base 2 of y. And so what we've done here is basically rewritten this logarithm in what I like to call compact form. We have expanded it out. Okay, and of course, we don't necessarily have to write the multiplication signs there. We could just rewrite it like this, and this would be our answer here. Let me make that look a little better. Okay, and so that would be our final answer. And so this concludes the final exam review for the Math 108 course. I hope this helps you all out a lot, and good luck to you on the final exam. Take care.